Hello and welcome to our third webinar in our educational webinar series, True Position, GD&T Basics, Referencing Datums. We originally hosted this live webinar on May 24th. However, due to some audio issues we had during the webinar, we chose to re-record it for our future viewing purposes. At the conclusion of the recording, Tom will be reviewing some of the answers to the questions we received during the live webinar, so stay tuned. So without further delay, we will get right into the subject matter. I would like to introduce today's presenter, our principal engineer and lead training instructor for ECM, Tom Kinnare.
Hi, thanks, Callie. Welcome back to the second try of webinar number 3, True Position, GD&T Basics, Referencing Datums. Quick word about the company before we get into the subject matter. East Coast Metrology, or ECM Global Measurement Solutions, is a metrology services company. We do a number of things: 3D scanning, laser tracker work, arm work, do some automation and systems integration work, and of course training. We've got a number of courses that you can see here. But what I really want to mention real quick is we're doing something new this year. We are doing the refresher course for the CMSC Level 1 certification test. And that'll be at the Coordinate Metrology Society Conference in Snowbird, Utah, July 17th through 21st. If you're coming to the conference and want to try to take that test for the qualification, you can take the course with us first. Maybe give yourself a little edge going into that test. Hope to meet some of you there. Okay, and you can visit our website for more details and information, or you can call us or email us. All right, today's webinar. First, we'll be talking about a few differences between basic and traditional dimensions. We're going to talk really briefly about orienting a part with a 3-plane datum reference system. We'll talk about the position tolerance as it's applied to a feature regardless of feature size or at maximum material condition. We'll calculate some position deviations, and we'll have 2 examples where we do that. 2 examples at RFS and then 1 example of position at MMC. I just used 1 reference today while putting this together, and that was ASME Y14.5 2009 edition. And mentioning a tolerance saying that's the current GD&T standard in the US. In the live webinar, no one had good references to recommend, so we'll just skip that. Okay, why are we talking about true position? It's very commonly called out tolerance type. It's an 80-20 subject, which means I can talk briefly, for this half hour, and you'll maybe get, maybe not 80, but maybe 70% of what you need to know about about true position in to do work, practical applications. Also, it topped the polls for what our webinar audience wanted to see. Okay, dimensions, comparing traditional and basic dimensions. Here we have a feature control frame, which is how we control, tolerances in GD&T. The first box, position tolerance, has the geometric characteristic. That little circle with the crosshair is, of course, the position tolerance indicator. Next, there's a diameter symbol. Sometimes that'll be blank, or sometimes you'll even have a small square there. That specifies the tolerance zone shape. Next to that, tolerance zone size. In this case, 10,000ths of an inch. Quite often you'll have a modifier of some sort here, modifier for the feature tolerance. Typically, probably most commonly would be maximum material condition. And then to the right of that, you have the datum scheme, primary, secondary, and tertiary datums from left to right. When we talk about true position, the way a lot of people use it is actually kind of a misnomer. True position is actually the ideal location of the feature, and what this symbol represents is really the position tolerance. Okay, kind of a side-by-side look. Traditional tolerances on front, basic dimensioning on the bottom. traditional dimensions run from feature to feature. And tolerances are attached to those dimensions. The tolerance zone shapes vary depending on the dimensions that locate the feature. In a GD&T basic dimensioning scheme, basic dimensions run from the ideal feature location to the next ideal feature location, or from a datum to an ideal feature location. The tolerances are attached to the features, and the zone shape varies according to the tolerance type, the geometric characteristic that was called out. Right. So, you know, an example of maybe a traditional tolerance zone, if you have this drawing on the left, you might think, right, default tolerance is plus or minus 5 thou. Right, you might think that you're getting a bunch of little 10 thou squares. That would be a tolerance zone in which you'd have to locate these holes. But because there's no hierarchy in a traditional tolerancing scheme, any one of those could be thought of as more important, or argued to be more important than the others, right? And you might actually end up, you know, being able to argue that this part would be right. And, you know, these tolerance zones vary. So, you know, this guy thought, okay, I'm starting with this corner, great. I've got a 5 by 5 zone here. You know, this next row up here is plus or minus 5 from there, so my tolerance zone is going to be 10 thou, plus or minus 10 thou tall, right? And the same sort of thing applies from left to right. He comes over, this next hole is plus or minus 10 horizontally, and then the third hole to the left is plus or minus 15. And that's called tolerance stack up. And you know, people can argue quite hotly about that if they don't think they're getting what they want. GD&T kind of cuts through all that argument. That's part of the purpose of it. You've got the datum schemes, which clearly shows you how you're going to line the part up, what's most important, where you're going to be measuring from, and then the tolerance zones are all a uniform size, you know, based around the ideal position for that feature. Another kind of benefit to using true position is for round holes and fasteners, a round zone best describes the limit of fit. If a designer is going to guarantee the parts still mate and he's using traditional tolerances, he has to actually give you a smaller tolerance than the GD&T designer would give you, right? And the GD&T guy, you know, not only is his number bigger, you know, he gets this little extra bit of yellow areas around the outside of the square here. You know, those are extra areas in which the center of the hole could fall. All right. A quick look at bolt circles with a traditional angle and diameter positioning. The zone is wedge-shaped, right? Because the angle is plus or minus 1 degree or half a degree, whatever it happens to be. So, you know, these two sides actually converge back on center, and then the tolerance zone radial distance varies depending on if you've got a radius calling it out or if you've got a diameter calling it out, right? Plus or minus 5 on the radius is going to give you plus or minus 5 ohm. Plus or minus 5 on a diameter is going to give you really plus or minus 2.5. So, you know, size varies depending on the way things are called out, and you know, the farther away you are from the center of your pattern, if you're plus or minus a degree, the farther away you get, you know, the wider that zone gets, kind of perpendicular to the radius. All right. Oh, going back, you know, with GD&T again, we've referenced the datum scheme. The zones are all uniformly sized based on how they want to fit together, you know, whatever the value the designer gave you. And they're all centered on the ideal position. There's no tolerance stack up. Okay. Again, you can't really talk about position tolerancing and measuring position without a look at datums. Gonna fly through this. If you want a more in-depth presentation, webinar number 2, we talked about planar datum systems. So a part has 6 degrees of freedom, and you kind of got to nail them down before you can measure. So there's 3 translations, 3 rotations, and in effect, they're constrained by the datums in a feature control frame. So here's a sample callout. I've got this L-shaped block. The bottom of my block is datum A. Datum B is this long edge. Datum C is the short edge. And the holes are all positioned with respect to A, B, and C. Okay. One way to think about setting up a coordinate system or a frame, the block goes and the datum A surface corresponds with the primary datum plane. It's going to take out two axes of rotation, rotation around this axis, and this axis is also going to limit translation up and down perpendicular to that plane, right? Then we would match the datum B side, the long side, up with our secondary datum plane. It's going to eliminate movement perpendicular to that plane. It's also going to eliminate rotation around an axis perpendicular to the primary datum. Last, the part moves sideways against the tertiary datum plane, and that prevents it from moving side to side in this view. So the part's fully constrained. Now we can measure. Okay. Position tolerances. Position tolerance is applied regardless of feature size, right? The hole can be too big, the hole can be too small. The tolerance doesn't really care if you're talking RFS, regardless of feature size. It uses a derived center line for holes or derived planes in the case of something like a slot or rectangular feature. The tolerance applies over the entire length of the feature, top to bottom. And it can come as a diameter or a rectangular zone, depending on if there's the diameter symbol here, or if it's blank or square. Blank or square being the same, and they mean it's going to be a rectangular zone. And typically, it means it only applies in one direction, horizontally or vertically on the print. Okay, just a quick look. Here's our part shown oriented to the datums, and with these green tolerance zones all the way down the ideal position of the holes. And the hole center line, as we measure it, has to fall within that green zone all the way up or down. Just a quick word on practical measurement practice. Obviously, you're going to have constraints on time, equipment, cost. So on CMMs, holes specified at RFS are often measured as circles at the top and bottom of the hole. Sometimes you don't have a probe that can reach. Threads are super difficult. And often we end up just trying to measure the minor diameter. Sometimes for both those cases, sometimes what you'll do is insert a pin and then measure that pin where you can get at it, and then extrapolate where the top and bottom of the hole would be based on the orientation of the pin. All right. Position applied at feature on a feature maximum material condition. The general idea of having a tolerance at MMC, it may be a little more work for the inspector, but it gives the manufacturer more room, more wiggle room to play with. So here, this would be an example. We've got our gray part. It's going to mate with these dark blue pins on the mating part. And so, a smaller hole has less room here than this bigger hole, right? So the bigger hole could have its location a little farther off, and the part would still fit together. That's the whole idea behind MMC. There's two interpretations for holes in MMC. There's the derived center line, or axis interpretation, and there's the surface interpretation. In the derived center line, the hole has to satisfy the size tolerance, and you start calculating this just like position at RFS. You still do the measurements the same way, but then you'll add a bonus position tolerance based on the diameter of the hole. Max bonus is limited by the size tolerance. If that hole is out of spec because it's too big, that hole is out of spec, and you don't get extra position tolerance based on that extra size bonus. You got to, if it happens to be too big and out of position, it's still too big and out of position. Though, if engineering or somebody dispositions that later, they may try to take that into account and use it anyway. but that's up to engineering, not us. For the surface interpretation, again, the hole must satisfy the size tolerance, and the hole must clear the virtual condition boundary centered at true position. Virtual condition is calculated as the diameter at maximum material condition minus the position tolerance. And that's for a hole. For a boss, that equation would be different. It seldom happens, but if interpretations conflict, the surface interpretation overrules the axis interpretation. I've never seen it, and most people don't even consider the possibility, but it's just something to think about. You know, you might bump into it you might bump into it on a job someday. Maybe you'll have a really tough customer who wants you to use surface interpretation or prove that your axis interpretation is good enough. And that can be a hard time. Okay, quick illustration of virtual condition. You know, we've got our tolerance zone, and you know, here's a possible location of the hole at MMC. But here's another possible location of the hole at MMC. The center could be just on the edge of the tolerance zone, and you know, your hole's there, and that part would be good. Or it could be at any one of these locations, right? So virtual condition then kind of describes that inner boundary of all those possibilities for a hole in MMC, right? And your part has to stay out of that, or it won't fit. So virtual condition is really a keep out area, right? And just, you know, a larger diameter can be farther from true position and still keep out. That's the idea behind the position bonus for MMC. All right, on to some examples. Example 1, here's our call out. We've got this 6-hole pattern to a true position of 14 with respect to A, B, and C. A is the bottom of the block, B and C are the sides, long side, short side, respectively. You know, that's pretty good. Here's our setup with our coordinate system. You know, arbitrarily I picked Z perpendicular to primary, Y perpendicular to the secondary, and X perpendicular to the tertiary datum planes. All right, we'll just say the hole center for this first hole, let's say it was measured at 0.504 from datum C, 0.506 from datum B. At the top of the hole, then all the way down at the bottom of the hole, it was measured at 508 from B and 494 from C. And so we're going to have to do the calculations twice to make sure that the hole is correct. Calculate the deviations from the true position. You know, you take your measured value for the position minus your ideal, your design value, the nominal value from the print. Then you do that for both X and Y. You calculate the radial deviation using the Pythagorean theorem. In this case, we come out to 0.0072. Of course, you have to double that, so you're comparing a diameter, measured diameter, to the diametral call out that was in the tolerance box. In this case, we get 14.4, so we're over, and we would be, probably rejecting this part, or at least suggesting, rework. That's a lot of work to do. If you've got software to do it for you, that's great. We do a lot of work with Excel and ECM, and we would just set up, a spreadsheet of calculations. We'd have our nominal positions for all our holes, and then we plug these formulas into these different columns for the X deviation, the Y deviation, the radius. X deviation be X measured minus X nom. Same for Y. Again, the Pythagorean theorem right here, and then we double that for the measured position and compare that back to whatever our tolerance was. Here we have it for the first two holes, at the top and the bottom of the first hole, rather. Showing that this hole is really not very good. And example of calculations for a hole, the complete set of holes, top and bottom, all 6 holes. If you want to practice, what you could try to do is just take a screenshot of this, cover over this whole right side, and then try to work this out and then compare it back to the screenshot if you want to try that yourself. Okay, example 2. A 6-hole bolt pattern, again, applied regardless of feature size. There's no modifier here next to the size. Yeah. Now, typically, it's hard to directly compare and calculate deviations based on a diameter and an angle. So what we usually do is convert it all to Cartesian coordinates. We're going to go in, we're going to do a little trig. Our coordinate system is set up. Datum A was the bottom of the block. It's a thin block, so I'm going to say it's not practical. The block is so thin it's not practical to measure top and bottom. We'll just talk about one set of measurements, but if we were doing a real job and the block was thick enough, we would do top and bottom. Other thing to notice here is, okay, so it's constrained to A, which was the bottom of the block, and B, which was B, which was this hole in the center, right? The datum scheme in our feature control frame doesn't fully constrain the part. And what that means is, in real life, we'd be able to rotate this part a little bit to make things look better because it's not fully constrained. Here's an example converting polar locations to the XYZ locations. Right. Again, our formula is going to look something like the nominal position is equal to the radius, which would be half the diameter if they gave us a diameter, of course, times the cosine of the angle, and the y would be sine. We typically, use the convention that our x-axis is going to be 0 degrees and our angle's positive counterclockwise from x. Not hugely important. You just have to make sure that you know what you've done and can keep track of it. All right. Then taking those nominal positions we calculated, we put those in the table, just like we did before for the rectangular example. We fill in our measured values, right? And we compare our measured positions, right? And we have this bad hole. But it's important to note the frame was not fully constrained, right? So we might be able to wiggle it a little bit to make this work. I like to plot the deviations of my holes, right? So these little purple circles represent the measured position compared to the ideal position of the hole. And if we look, most of these holes are off in a counterclockwise direction from where they should be. The 2 that weren't, hole number 1 and hole number 6, were still really good. They're really close to their position. So, we might be able to rotate our frame a little bit and think about this a different way. The tolerance on these 2 will get a little worse. The tolerance on the others will get a little better. And redo the calculations and see if it fits. I'm not going to actually do that to save time, though. So I leave that to you if you want to do it. Okay, example 3. We're just going to talk real quick about trying to calculate tolerances, whether or not a part conforms when tolerances are applied at maximum material condition for the feature. The procedure for datums is different. Don't try to take this procedure and use it on datums. And that's a whole other subject, a little more complicated, and there's a few extra things to think about. So we're just talking about features right now. In this case, we have our call out, and our tolerance is 10 thou at maximum material condition, and we're just talking about this one hole out here. If you have multiple holes, you just do the same thing a lot, many more times. Okay, the call out in words, right? What this means is the position tolerance zone, right, with respect to datums A, B, and C, is 10 thousandths in diameter, got our diameter symbol, when the feature is at maximum material condition. So the smallest hole would have this tight tolerance. As the hole gets bigger, the tolerance zone expands. We typically call that a feature bonus or a size bonus, tolerance bonus. And as the feature departs from MMC, varies from MMC, gets bigger, we get extra tolerance. Okay. So for a hole, MMC is the smallest hole size, smallest hole diameter. MMC is always calculated from design dimensions and tolerances. I have seen people try to calculate MMC using measured values, and it's just going to lead to heartbreak. And the hole size at MMC is going to be equal to your nominal diameter plus the lower tolerance. All right, so in this case, our nominal diameter, 358. Our lower tolerance would be -2. Right? Our tolerance is plus or minus 2, so -2 would be the lower tolerance. So 358 plus -2 is 356. So that's our MMC condition. Again, we often use Excel tables. If you got software that does it for you, excellent, great. But if you have to come back and deal with the data yourself, Excel's a great way to do it. I've set this up, but the first 9 tables are the same. And something important to remember, if you pass at RFS, you're going to pass at MMC. We add columns, and then we add these extra columns over here for MMC and bonus calculations. All right, going through here, our measured values. We measured 360 instead of 358 on the diameter of the hole. We measured 690 instead of 693 up from the x-axis. We measured 1 inch 34 thousandths instead of 1 inch 40 thousandths. And we see the math down here, right? Our x was 6 thou off. Our y value was 3 thou off. The radius, that works out to about 7, a little over 7. But we've rounded here in the table. So our measured position was 13. I'm sorry, it's a little less than 7. Rounded off there, but it shows up here as 13. Our position tolerance was 10. Hole diameter was measured hole diameter, that was 360. Our MMC hole diameter is 356, so our size bonus is going to be 4 thou. Take our position tolerance plus that bonus, gets me a 14 thou, and the part's going to pass because it was only out 13 thou. All right, then we went into question and answer. We get a free bonus here because I was able to prepare some slides that address the answers to the questions instead of just having to try to talk the answer through, as I normally would have to do. So I guess that's one advantage of re-recording this webinar. So we'll get right into that. First question was, what if I need to report the measured angles and diameter for a bolt circle? Okay. Right, so we measured our holes and we recorded that data as XY. You just do the same calculations backwards that we did to figure out where the nominal position of the holes in XY coordinates was from that kind of polar coordinate system that we were originally given. Typically, we calculate the radius with Pythagoras, square root of the sum of the squares of x and y, the measured values, because we're going to report measured values, of course. And then that took time to double that to calculate the diameter, because this callout was against the diameter, so I'm going to want to compare directly to that. And then I've got this angle, right, and that'll be the arctangent of the measured value of y divided by the measured value of x. All right, so that's how you would get back, so you could compare directly to the numbers that were on the drawing. Okay, next question. If a drawing follows the ASME Y14.5, do you have to report basic dimensions, and what standard dictates that? Okay, yep. Good question, a source of argument a lot of times between customers and the guys actually doing the measuring. Y14.5 doesn't explicitly define any reporting requirements. and it's often a source of confusion between metrologists and their customers, be it engineering, quality, or a different company. To try to address that, there's a subcommittee of Y14.5, the Y14.45 committee. I'm actually sitting on that committee now. We're getting really close to releasing this spec. And in general, it's going to set 3 levels of reporting that the customer would specify. Method AB, which would just be a pass-fail report. Method B, which would just be a single number comparison back to the design tolerance. If they specified method B, you wouldn't have to report the basic dimensions back to them, the measured values for those dimensions. And then method C is method B with additional customer-defined information. So they would have to tell you exactly what they wanted. Again, the idea is to try to clear up any confusion between the guy doing the measuring and his customer. Also, I'll just take a mention here. Don't forget uncertainty in determining whether or not a feature conforms. That's all I'm going to say right now, but it is an important thing to think about whenever you take any kind of measurement. What's the uncertainty of my measurement, and how does it affect what I say about my result? Okay, the third question, is a true position of a bore through a plane the same as perpendicularity? And someone else had asked, is there a formula for including perpendicularity in true position? Typically, the primary datum plane is let me back up. Typically, your hole wants to be perpendicular to your primary datum plane, and that's either going to be like the bottom of a block or the top of the part, right? The holes are going in perpendicular to that. Now with position tolerances, the whole center line has to fall within the cylindrical tolerance zone, running all the way up and down, and that zone by definition is perpendicular to the primary datum. So that's going to limit the perpendicularity of your hole to that datum plane, right? Because you can't get too crooked, or you'll come outside of the position tolerance zone. If perpendicularity is really important to the designer, and he needs a tighter control than the control that's kind of inherent in the position callout, he can add a second line to that feature control frame. He can add another segment down here with a perpendicularity callout, and and that should be tighter than the position tolerance. All right, and question number 4. How would you check true position for holes oriented in 3D, like holes on an aircraft cowling? Here I've got my aircraft cowling with my nominal position, and then I've got 2 measured points in that hole, trying to establish where it is and what its orientation is. Procedure stays the same. You're going to lock into datums. You're going to measure the hole. You're going to find the 3D distance from your measured points to the nominal center line. So this measured center at the top, measured center at the bottom. I need to find the 3D distance back to my nominal center line. A lot of people are lucky. They've got software that will do that. If you can't do it, then you need to use Excel. The formulas are kind of involved, more so than I want to go into here, because it will take some time. And as always, you report the worst of the 2 points. That is the webinar. Thank you very much for coming back to listen to it. If you were here the first time, I apologize for our sound issues. Hope this one is nice, clear recording. And thanks again.